Thank you, Mr. Bart, for the invitation. Thank you, everyone, for coming. Here is our first example of a mathematical game. You see a grid with 4 rows, 5 columns, a rook taken from a chess set, and a special square containing some cash. You have 2 players, Alice and Bob, and they alternate turns in moving that rook. First goes Alice, then Bob, then Alice again, and so on. The rule is that the possible moves of the rook are horizontally right or vertically up. It's not quite the same rook as one from a chess set, because it can only go horizontally to the right, never to the left, and only up, it can never go down. They alternate moves. What is the goal of the game? The player who first hits that special square containing the cash wins the game. Okay? So they alternate turns, move the rook, and you want to be the player who first hits that cash. Now it is Alice's turn. What is Alice going to do on her first move? This is the question that we'll answer shortly. First, let's begin with an easier question. What is Alice not going to do on her first move? That's easier. Alice figures out that she's not going to bring the rook all the way to the right. If she brings the rook there, then Bob immediately hits the cash. So this is a bad move on Alice's side. She's not going to play that. Similarly, she's not going to bring the rook all the way up. If she does, then Bob will take the cash. At all times, if you're playing this game, you want to avoid the boundary. If you place the rook at the boundary, your opponent can win. So you figure this out. Alice is not doing any of these 2 moves. Where is she bringing the rook? Maybe she considers that move. Okay, she moves the rook there. Now it is Bob. Bob also figures out that he should avoid the boundary. So he's not going right, he's not going all the way up. There are really 2 squares left. 1 square up or 2 squares up. If you're Bob, where would you move the rook at this point? 1 or 2 squares up? Yes? 2 squares up. Very good. Bob moves the rook 2 squares up. Now it is Alice's turn. And Alice figures out that she's going to lose that game. She is now at a losing position. She is the active player, the player who is about to make a turn, but she is helpless. Regardless of what she does, namely moving it 1 square to the right or 1 square up, Bob will win the game. So Alice loses this particular game. Notice, if we look at the rules, that this is a perfect information game. There are no cards hidden, there is no throwing of dice, and both players know everything about the game. Also, there can never be a draw. One of them, sooner or later, will hit the cash. As you keep moving the rook, it gets closer and closer to that target square. This is a mathematical game. All the games today will be of this type. Okay, and these games can be analyzed systematically. So let's perform systematic analysis of the game until we reach complete understanding. So we start with just the cash without the rook. And then we place the rook first at that square. We already observed that if it is now your turn, then you are at the winning position. You just immediately go and hit the cash. Okay, if the rook is here and it is your turn, then you can win no matter how your opponent plays. We say that you're at the winning position. Of course, if it is your turn, then you can also lose. If you move the rook 1 square up, you make a stupid move, you can also lose. That doesn't matter. The important thing is that you can win no matter how your opponent plays. And let's mark this. Let's put a plus. The plus indicates this is a winning position. You want to be the active player if the rook is there. You want to be the player to make a turn. Now let's mark other squares which give you winning positions. Everything on the boundary is a winning position. If the rook is on the boundary and it is your turn, then you can win. Now we continue with the table. Remember when the rook was there. It was Alice's turn. And she was stuck. She was helpless. No matter what she does, she brings the rook to the boundary. You don't want to be the active player when the rook is there. So, if the rook is here, and it is your turn, then your opponent can win, no matter how you play. We say that this is a losing position. Alice was at that losing position. That's why she lost the game. And we mark this by putting a minus. We did this already in the analysis of our sample game. Now we just record our easy observations, put them on the table, and we continue completing it. When the rook was here, remember it was Bob's turn, and as you suggested, Bob will move the rook 2 squares up. Bob is very happy to be at that position, because he has the option to move the rook 2 squares up and bring it to a minus. A square already marked as a minus. So once Bob has that option, he is at the winning position. Okay? So there exists a move to a minus. There also exist stupid moves, 1 square to the right or all the way up. But the important thing is that there exists a move to a minus. Bob has a way to screw up Alice, to bring the rook to that minus. Therefore, the active player right now is at the winning position. We indicate this by a plus. This is exactly the work that we had done when we analyzed the sample game. But now we continue with the table. Every square from which you can reach that minus is likewise a winning position. All of these are pluses. If the rook is there and it is your turn, you bring it to the minus and you screw up your opponent. Okay, next. What if the rook is here? Yes?
This person is also going to lose.
The active player, the player who has to make a turn, is going to lose if their opponent plays correctly. Indeed, because why are they going to lose?
Because no matter where he goes, he always ends up on a plus.
Exactly. No matter where they go, the rook will hit a plus, and your opponent will be at a winning position. You put your opponent at a really favorable, really nice position. So here, every move leads to a plus. No matter what move you make, you will bring the rook to a plus, and your opponent can win. Therefore, this is a losing position. And again, every square from where you can reach that minus should also be a plus. If the rook is anywhere there, in one move, you bring your opponent to the minus. You just continue. When the rook is there, same thing. No matter what you do, your opponent will end up at a plus. So you have 6 moves available, but none of them is very attractive. This is a minus. And finally, we arrive at the initial position. From the initial position, you have the option, Alice has the option to move the rook 1 square right and bring Bob at a losing position, bring Bob at a minus. Therefore, the initial position is a winning position. And Alice has a winning strategy. So Alice has a way to win no matter how Bob plays. Please keep in mind this picture with the pluses and minuses. From a minus, every move leads to a plus. That's what it means to be a minus. You have no good move. With every move, you bring your opponent to a favorable position. To be at the plus, you have the possibility to win no matter how your opponent plays, means there exists a move that brings to a minus, leads to a minus. And notice, by the way, Alice's strategy is very easy to describe. On her first move, she goes to that diagonal of minuses. Then Bob goes away from the diagonal, and Alice brings the rook back to the diagonal. If Bob goes right, Alice will go up. If Bob goes up, Alice will go right. And it is always Alice who brings the rook back to the diagonal. Bob moves it away from the diagonal. Therefore, Alice will first hit the cash. Notice also that Alice can tell her strategy to Bob, and she's still going to win. It's not that she has to hide the strategy. She can openly tell Bob, listen Bob, I go to the diagonal, then no matter what you do, I come back to the diagonal, I win. So she can very well tell her strategy to Bob, and Bob can still not do anything. By the way, if Alice and Bob are in this room, they're not going to play the game. It's now boring. These games are only interesting to analyze. Once you have now we have complete understanding of that game. It's no longer fun, so we move to the next game. It's called Nim, and you start with a pile of 9 coins. Alice and Bob alternate turns in taking coins, as the name of the game suggests. First goes Alice, then Bob, and so on. On each move, a player can take either 1 or 2 coins. So if it's your turn, you decide if you want to take 1 coin or 2 coins. The goal: the player who takes the last coin, the player who finishes the pile, wins. You have to decide on each move if you take 1 or 2 coins, and you want to be the one to finish the pile. Let's look at the sample game. On the first move, Alice, let's say she takes out 2 coins. There are 7 left. Then Bob takes 2 coins, there are 5 left. Then Alice, maybe she decides to take out 1 coin, there are 4 left. Now it's Bob. And Bob starts to think. Now it's fewer coins, and it's more reasonable, easier to think. He figures out that if he takes 2 coins, then Alice will take the last 2 coins and win. So Bob doesn't want to take 2 coins. Bob takes out 1 coin, there are 3 coins left. Now it's Alice, and Alice is not very happy. If she takes 1 coin, Bob will take the other 2. If she takes 2, Bob will take the last coin. In any case, now Alice realizes that she's going to lose the game. She takes 1 or 2 coins, there will be 2 or 1 respectively left, and Bob can win in either of these cases. Okay, so Bob wins this particular game. Let's start analyzing the game again. We analyze going backward. You see, when there are fewer coins, it's easier to figure out what's happening. If there are 2 or 1 coins, you want to be the active player. This is a winning position. If there are 2 coins and it is your turn, then you can win. We put a plus. If there are 3 coins, this is a minus. You don't want to be the active player. If there are 3 coins and it is your turn, then you're going to lose. No matter how you play, both possible moves go to a plus. If there are 4 coins, as Bob observed, Bob was now at the winning position, because he had the ability to take out 1 coin and bring Alice to this unfavorable losing position with the minus. Remember, from a plus, there exists a move to a minus. How about with the 5 coins? Is it a winning or a losing position? Plus or minus, yes? Sorry? Winning position. How many of you think it's a winning position? Okay. How many think it's a losing position? Okay, it is a winning position. Why is it a winning position? You could take 2 coins. Excellent. So this was a possible move. Alice didn't play that move, but that's her problem. The position itself is a winning one. There exists a move that goes to a minus. Alice could have taken that. So this is very much a winning position. Thank you. Notice, Alice played the wrong move, going from a plus to a plus. she should have taken 2 coins directly, bringing Bob to this unfavorable position with 3 coins. This motif will show up again in the last game. Alice could have interchanged who the active player is in this 3-coin position. Okay? So there were 2 moves being played, from 5 to 4 and from 4 to 3 coins, but Alice could have taken directly 2 coins, bringing Bob to this minus position with 3 coins. Because there exists a move to a minus, it's a plus. Okay, now very easy, we can analyze the game and figure out if at the beginning Bob or Alice had a winning strategy. 1 or 2 coins is a winning position, you want to be the active player. 3 coins is a losing position, you lose. 4 coins, there exists a move to a minus, therefore you're in a favorable position. It's a plus. 5 coins, again you have the possibility to take out 2 coins and bring your opponent to a minus, to that unfavorable 3-coin position. Alice didn't take advantage of that, she took out 1 coin, but 5-coin position is a winning one. 6 coins, every move leads to a plus. There are 2 moves available and both of them bring you to a plus. So this is unfavorable, losing position. With this guideline, you just complete the table, starting from the simpler positions and moving on to the more complicated ones. With 7 or 8 coins, you have the possibility to bring your opponent to 6 coins, and 9 coins is again a minus. Every move leads to a plus. So, Alice, the first player, or Bob, the second player? Who has a winning strategy in this game after all? Yes? Bob. Bob has a winning strategy. The initial position is with a minus. The initial position is unfavorable. Minus means that your opponent can win no matter how you play. The initial position, it was Alice's turn. Alice was the active player. So Bob can win no matter how Alice plays. Notice that the minuses are at the positions divisible by 3. If there were 99 coins, again Bob would have a winning strategy. If there were 100 coins, Alice would have a winning strategy. And again, the strategy that Bob has is very easy to describe. If Alice takes 1 coin, Bob will take 2 coins. Altogether they take 3, and this brings Alice again to a minus. If Alice takes 2 on any of her moves, Bob will take 1, and this will again bring Alice to a minus. And again, notice, Bob can tell Alice her strategy. Bob can tell Alice his strategy, and still win. He can very openly tell her that whenever she takes 1 coin, he will take 2 coins. If she takes 2, he will take 1. Alice knows that, and this doesn't help her. Okay, this is the game of Nim. The last one is more subtle. It's called chomp, which means to bite. Alice and Bob, this is now a bar of chocolate. Our friends alternate turns in biting chocolate blocks. Alice goes first again. The rule is as follows. On each move, a player chooses a block and takes out all the blocks northeast of it. All the remaining blocks that are above or to the right of the chosen block. We'll do an example in a second. What is the goal? The player forced to take that dangerous sign square loses. So you want to avoid that bottom left square. If you are forced to take it, you lose. Let's look at the sample game. Alice, on her first move, chooses that square. Along with that, she takes the whole block northeast of it and chomps it, bites it. Then Bob, maybe he wants this square. Together with it, he chomps everything above. Now it's Alice. The green circle indicates the active player. Alice takes this one. Together with it, she takes everything remaining to the northeast. It's not a rectangle remaining anymore. Whatever remains, she takes it out. Now it's Bob, takes this. Now it's Alice, She chooses this square. Together with it, she chomps that whole piece. And now Bob figures out that he can win. Bob just takes out the rest. Alice is the active player. She is forced to take the dangerous square, and Alice loses. So Bob wins this particular game. Okay, let's go back to the original. By the way, these possible configurations with staircases are the possible positions in the game. If you were to perform this backward analysis that we did, you have to assign to each such staircase a plus or a minus. You start with the ones with fewer squares, and then you build further and further positions, more and more squares, larger staircases. That's not what we're going to do. This is too complicated. We're not going to do backward analysis in this game. Okay, so these are the possible positions. I claim that Alice has a winning strategy in this game. We're going to prove that Alice has a winning strategy without doing this backward analysis. Backward analysis would be possible for a specific grid, but it's too complicated. There are too many positions to consider. In fact, Alice has a winning strategy regardless of the size of the grid. Even if it's 100 by 2000 squares, Alice always has a winning strategy. Okay, we're going to prove this claim. It's a beautiful, non-constructive proof. We will prove that Alice has a winning strategy without giving any idea of what that strategy is. It is just an existence statement. It's a very subtle argument. How can you prove that something exists if you cannot show that thing, if you cannot display it, cannot exhibit it? Alice will not know her strategy. She will only know that she has a winning strategy. Let's say you're in the train and the ticket controller comes, and you have to prove you have a ticket. Can you prove that you have a ticket without exhibiting your ticket? Very difficult. In this case, however, we can prove that Alice has a winning strategy without exhibiting her strategy. How do we do that? Well, by contradiction. It's either Alice or Bob who has a winning strategy. So suppose, for the sake of contradiction, that it is Bob who has a winning strategy. You agree, the initial position is either plus or minus. Either the first player has a winning strategy or the second player does. If you imagine that you perform this backward analysis, it would be tedious, but it's possible, you will arrive either with the plus or with the minus for the initial position. So suppose, for the sake of contradiction, that Bob has a winning strategy, that is to say, the initial position is a losing position. Alice's opponent, Bob, can win no matter how Alice plays. What does that mean? What does it mean that the initial position is a minus? What do we know for a position marked by a minus? Yes?
When your opponent knows how to play the game, you will lose.
Yes, if your opponent plays correctly the game, then you are going to lose. But what about the possible moves from a minus position? What do we know about them? Yes? It always leads to a plus. This was the punchline, heavily emphasized today. Every possible move leads to a plus. Very good. We're going to apply this observation to one specific move. To the move where Alice takes out the top right square. So we know that every move leads to a winning position. No matter how you play, you're going to bring your opponent at a favorable position. Therefore, this particular move brings Bob to a winning position. This is a plus. What do we know about the winning position? Now Bob is at the winning position. This is with a plus. What do we know about the moves that Bob can make? What does it mean to be at the winning position? Yes?
There's a possible move to bring the opponent to a minus.
Genau, there exists a move to a minus. So now Bob is at the winning position, so he has a way to bring Alice at a losing position. So there exists a move leading to a minus. We don't know where this move is. It could be any of these squares. So let's say it's like that. Remember, we started with the assumption that Bob has a winning strategy rather than Alice. Our goal is to derive a contradiction. We have to get the contradiction. I claim what we have right now on the screen is absurd. There is a contradiction here. Does anyone notice a contradiction? Yes?
The one who started this now, I think, is Alice, is able to win. It's on a plus.
Wait, so there exists a move to a minus, so this is a minus. Okay? And so what is the contradiction? There is a contradiction. What we have on the board right now, Alice starting with a minus, then taking out the top right, bringing Bob to a plus. Then Bob has a move to a minus, maybe this 4x2 block, bringing to a minus. Now, what we have on the screen is impossible. Why? Yes?
I guess this thing could have been reached with the first.
Excellent! This last position could have been reached already by Alice's first move. This was a possible move. Remember with the NIM game from 5 coins to 3 coins. This is a possible move. How is this possible? From a minus there exists apparently a move to a minus. This is not allowed. From a minus, every move should lead to a plus. So therefore, this is a contradiction. The contradiction was due to our assumption that it was Bob to have a winning strategy rather than Alice. Therefore, after all, Alice must have a winning strategy. See, let me phrase this argument in slightly different wording. The same argument, just different presentation. Suppose that Bob has a winning strategy. And then Alice goes and tells Bob, "Hey Bob, I know that you have a winning strategy. I trust you completely. This is a mathematical game. It will not hurt if you share your strategy. Can you be so kind to tell me, if I were to take the top right square, I'm not going to take the top right square, but if I were to take the top right square, how would you win? Would you please share your strategy?" And Bob says, "Yeah, sure, Alice, why not? This is a mathematical game. If I tell you my strategy, you still cannot do anything. If you were to take the top right square, I would take that 4x2 block," and then he shows her the whole continuation of how he can win, no matter what she plays. So, if you, Alice, were to take the top right, I would take that 4x2. And then Alice says, "Oh, thank you so much, Bob. So nice of you. You're such a nice guy. I really appreciate it. Actually, I changed my mind. I'm not going to take the top right. I will take that 4x2 that you just pointed out. And I will use the same strategy that you were thinking to apply. So I'm going to win by using that same strategy." Therefore, if we assume that Bob has a winning strategy, then Alice has a way to steal his strategy, and she also has a winning strategy. That's a contradiction. They cannot both have a winning strategy. This is a beautiful non-constructive proof, but don't do things like this in the train when you are asked for your ticket. Thank you.